Okay, we'll get to what the tip of the month was the TVP and RVP issues and solutions. So vapor pressure, it's going to be a function of the composition, temperature, pressure, and then how long the crude's been there, the residence time, whether it reached equilibrium, whether it's been sitting in the tank and it's essentially down oil, dead oil. And it's the molecules mainly with the associated gas, ethane, butane, propane, that are raising the vapor pressure, escaping the liquid, and those the kinetic energy of those molecules is creating the pressure above the liquid. So anyway, I thought this was kind of interesting. The models I'm going to show you are based on an Eagle Ford crude with 1,000 GOR, but this is a picture from the internet of an Eagle Ford crude, and all the technician has done is take it from a screwed top glass bottle and poured it into a graduated cylinder. And you can see just transferring the fluid's not stable. It's boiling, it's degassing, and that's exactly what the types of fluid that we're dealing with. Most unconventionals are dealing with light oils like this. The Bakken oil is a light oil like this as well. They're like mineral spirits. Real busy slide. You can look at it later, but it's a parametric analysis, and the summary is here. The vapor pressure is going to increase if the pressure on the heater treater increases. So the model's down here, and it's just a heater treater and a tank, an oil tank and a water tank. The vapor pressure is going to increase if the temperature decreases. The molecules condense. And the vapor pressure is going to go down if the GOR goes down. And these two cases are summer and winter for a 400 and summer and winter for a 4,000 GOR. And we're increasing the treater temperature this way. We're looking at the RVP here, and then increasing the pressure that way. But the summaries are right there, just to give you a feel for what we're talking about. The difference between the summer and the winter cases had the stock tank at 40 degrees Fahrenheit, and the summer cases had it at 80 degrees Fahrenheit. So looking at the phase diagram for the reservoir fluid, which was at Eagle for 1,000 GOR, you can see that it's not a black oil. A black oil would have had a big nose, and so it's more like a gas condensate. The other thing when you're looking at these is check the temperature and pressure and look at the ranges. So if that's 600 degrees, you're clearly looking at an oil, it's not a gas. Now we'll look at a gas. You can see the temperatures are much lower. This is the gas that's going to come off the vapor cover system. Okay, and if you look at it, 45% of it is ethane to butane. Also, the molecular weight of the gas is really high. It's heavier than air. So if this is coming out of your tanks, the thief hatches are open, it's going to fall to grade, and the heating value is like rocket fuel. It's very high. The gallons per 1,000 cubic feet, if you could recover 100% of the molecules, it's very, very rich gas. In fact, it's so rich that this green quality line is 50% liquid. So once you hit the temperature and pressure and cross that line going from the left, or from the right to the left, half the liquid's going to condense. So if you're operating this particular set of molecules is prone to infinite recycling, and this is what you're seeing in your vapor recovery compressors. I've also included, this is the tool that generated that. You input the gas analysis. I've used this tool for years, and it does some pretty cool stuff. One is it double checks and normalizes your gas analysis to 100. A lot of times there's a few trace components, and you can just go down to C6, put this in there, and it'll, for example, this is the sales gas, and it's still fairly rich gas to be using if you're going to use that for a compressor. And this is what the sales gas looks like. Again, the 50% quality lines moved way to the left, and the turquoise line's the hydrate line. And this is what the sales oil looks like. This is a Unisim result of a heater treater to a stock tank. So we're operating at 120 Fahrenheit and 65 pounds, and we're ending up at 110 degrees Fahrenheit in the stock tanks. The black numbers are pound moles, but just to give you an idea of the relative volumes coming out of the different places. So this 2 pound moles an hour, that's causing all the problems with not meeting vapor pressure. The other thing that I want to highlight here is that HYSYS or Unisim are single point solutions in steady state. So it's at the vapor liquid equilibrium. Okay, it's not a measure at the bottom of the tower or the bottom of the tank. And in this case, we're fine. We've got a true vapor pressure that we can sell the crude oil, no problem. This is a battery in the Bakken. You've got the direct fired stuff, which is the hot stuff, all the way away from the stuff there are the stock tanks. And it gets pretty cold there. And all the piping's at grade, although you can't see it. So in the summertime, this works really well. The only problems that the design has are that the tanks are bottom fed, so you have the hydrostatic head of the liquid in the tank adding to the vapor pressure because the tanks aren't perfectly mixed, perfectly stirred. It gets oxygen in the system, just to breathing with the tanks, and you can also lose revenue if you're operating too hot. So you really should be looking at optimizing the vapor pressure with the temperatures in your system. It does meet the TVP and RVP, and the other thing is because the tank is bottom fed, there's no static issues to cause ignition in the tank. But this is boiling water when it's 30 below, so it just even sounds painful when you hear him walking. So in cold climates, if your stock tank starts at 110 Fahrenheit, how cold does it have to get before you're going to have vapor pressure issues where your crude won't meet vapor pressure? And that's fair. I mean, you're not running the simulator. It's hard to tell. But most people would think it has to be pretty cold. The correct answer is 90 Fahrenheit. So you have the equipment, the hot stuff, way far away from the cold stuff, and all the pipes uninsulated. And what happens is that little packet of fluid that starts here at 50 pounds and 120, it's still in the pipe, but it never gets to the tank to make the final flash at 110 in atmospheric. You got the head of the tank, and even if you're here at the top of the tank, with this particular fluid, 90 Fahrenheit, you'll bust. You won't make vapor pressure. And that's not wintertime. That's not very cold. In most places, we get a lot colder than that. So this particular design also has an issue with internal reflux. So if you do heat the tanks and it's minus 20 out or 0 or 40, propane and butane are going to condense on the shell and never make it into the vapor recovery system, and it's going to fall down, and it's a dynamic problem. It's going to continue to build in the system. So, you know, do you heat everything? Do you insulate everything? When you compare this with the drawing of the normal unconventional battery, there's a lot of equipment to insulate if you wanted to keep it warm. The good news is you don't have to do that. It's kind of a redundant curve, but I want to just make the point with the cooling curve. We're dropping the pressure and the temperature going this way from the treater to 0.3, and we've got to get it above 90 Fahrenheit with this fluid at 14.7 pounds up. So there's absolutely no way for that design to work when it's cooler. How does oxygen get into the system? Well, the vapor recovery system can go down. A lot of people put their piping at grade and the lines are pocketed. So you can block it with ice or block if there's a flame arrestor if it's going to an emission control device. The tank's over pressure, the heat thief hatch opens, and you get air into the tank. And this can be tied to a vapor recovery system or a flare. You really need to blanket your tanks, guys. Some operators are relying on no blanket gas and just auto. The oil gas evolution is going to provide blanketing. Well, you may be okay now, but when the rates go down low and you're down to 10 barrels a day and your water tanks are going up and down and they're all manifolded together and you've got H2S and iron sulfide in the roof, you got an ignition source, you got oxygen coming in the system, and you're going to blow the tanks up or have a tank fire. This is why wastewater plants have more of a tendency to catch fire than oil batteries. So what's the solution? Well, one solution is a vapor recovery tower, and I'll show you what's good about it and ways to improve it. So typical well through the separator, through a heater and a heater treater, you get to this vapor recovery tower, and I'll show you what it is and how it works. But it actually sets up a pressure barrier with a U-tube between the tower and the stock tanks. So there's absolutely no way for oxygen to get into the gas plant. And the other benefit is all the gas comes off the VRT, and theoretically, no gas comes off the stock tanks. So you'll meet quad 00, the tanks won't be venting, and you won't have to mess with the tanks operationally. You'll be making vapor pressure all the time if you do what I'm going to show you on the VRT. So the VRT tower itself operates at 1 to 3 pounds. It's a meter in diameter, 36 inches, 35 foot tall, and the height is just to get enough head height so that you can get into your 20 foot tall storage tanks. So what I'm showing here is if your treater conditions are this and you keep this warm, you're not going to have any problems meeting vapor pressure in your tanks, because right here you're meeting vapor pressure. And at 0.3, you can put in a gas buster. I'd recommend it, because that's your last chance to get the flash without the tank head. This allows you not to have a problem with static. And then another design note is you don't put this back into the tank. We're trying to get all the LPG out and away from the system, so you got to make sure that it doesn't fall back in the tank with your piping setup. But this solves a lot of the issues. The big economic benefit of this, if you put the VRT close to the treaters, you only have to keep these two vessels warm. I'd still insulate the line and keep the gas boot warm because it's your last chance, but you don't have to insulate or heat any of your tanks. All your tanks' vapor pressure will be fine. Another design I like a lot is a heated gun barrel tank. It works just like the VRT, except it's not a pressure vessel. So you can have a lot larger mass to try and keep warm, plus have an externally supplied heat to it. Has all the same features of a VRT. But looking at the Unisim presentation for this slide here, the key is keeping it hot and keeping the pressure low. And if you do that, you're going to meet the vapor pressure there, which is going to, once you've met the vapor pressure, it doesn't matter how hot, cold the fluid goes from there. In fact, in this, the process engineers will understand this, but I took it down to minus 40 Fahrenheit, and the vapor pressures are still going to be the same. So you don't have to worry about winter anymore. And also, in this simulation, you can see there's no gas coming off. Gas will only come off if you exceed 100 degrees Fahrenheit here. You'll start to evolve gas. This is high bond. This is what their VRT looks like. Supplies feed at the top. They're getting the flash at the top. This is another one from Jesco, except all the lines are coming in from the bottom and they're supplying some heat. They said they were using vapor recovery compressor exhaust to provide the heat. And the reason the line's coming from the bottom, they said so that you can insulate it. This is what they look like. Now, based on what I've just shown you with Unisim and science, none of these designs that you're looking at right now will work in the wintertime because these are pin fins and there's no insulation at the top, no way to supply heat at the top. It looks like they may have tried to supply heat in the bottom of these towers. And that's why I say you're probably better off to use a heated gun barrel tank. I'm not recommending that you use a direct fired gun barrel tank because the next thing we're going to talk about in a few minutes is the failures of the fire tube. You could have a fire and light a problem with your battery. This is from civils, and I've included the civils in the Dropbox. But it's just this, and they're old. These were old when I was your age and started. I mean, they're from the 60s, but they're good go-bys, and it'll show the relative capacities you can get with a gun barrel tank versus a heater treater versus a comparison with a single VRT of 2,000 barrels a day. So I'd encourage you to consider VRTs or gun barrel tanks. This is something I pulled off of LinkedIn. There's a facilities engineer named Moose Adams, and he indicates that after making some very substantial process changes in our field, we were having issues with excessive gas breakout in our tanks, so much so that the shell was literally shaking. The solution was a modified gas-liquid Cyclonic Separator to act as a degassing boot upstream of the tank. And that's a really good idea. All you need is some type of device on the piping to disengage some gas and insulate it. It doesn't have to be this elaborate. And an improvement they could make for the wintertime is to heat and insulate that to get that last flash. Another thing to look at is your vapor recovery system. You don't ever want to recycle and send those liquids back from the suction and discharge scrubbers back to the tanks. That's the material that's causing the vapor problems. So you either have to operate this separator hotter so there's no liquid to condense and send it this way to the fuel, or to pressurized storage. So if you look at this is the vapor recovery phase diagram for the vapor recovery gas, you're going to have to operate here hot. And again, you don't like to operate hot because you lose compression horsepower, and there's a limit to how hot you can get before you start to have problems with the seals and the compressors. But if you don't do that, you're going to condense liquids, and then you have to put them someplace. If liquids do condense, I'd recommend on this separator here to use a positive displacement gear pump, Moino pump, progressive cavity pump, not a centrifugal pump. You'll tear seals up. The other options are condensate stabilization. These are two 20,000 barrel a day stabilizers. This is from one of the Campbell courses, and it shows you the operating conditions that the stabilizer can operate at, and that way your fluid will meet real low vapor pressures. Anadarko who's installed about 300 VRTs, now is using a tankless design. I'll show you what that is. They have satellites. The satellites have separators with meters going to pipelines, and then they send those off to a centralized oil treating facility. This is an aerial view of what those satellite sites look like, where they have separators, multi-phase meters, and everything goes off to a central facility. In West Texas, it's easier to run pipelines than it is in some other parts of the country. But what this does is it eliminates tank venting and all the truck traffic. Another thing you can try is if from your heater treater and it's wintertime and you've got a VRT or a stock tank and it's all cold, in this case it's at 0 Fahrenheit, you can use a vac truck, because once you pull a vacuum on the fluid, it's going to boil, and that's the other variable you have to adjust. So in this example, although all the fluid was at 0, I took it down to with a vacuum of 10 pounds. Most of the vac trucks can go down to 28 inches of mercury. So again, the downside of this is you don't like to have vacuum for oxygen egress when you're dealing with hydrocarbon systems. But if you can anytime you transfer this fluid, when the vapor pressure is high, it's going to be degassing and boiling anyway. So if you could get a 1% increase in oil for 100,000 barrel a day field, and you're adjusting your heater treater pressures and temperatures so that you're not boiling up too much, or that you have the vapor pressure right, that's 1,000 barrels a day, 365,000 barrels a year. At $100 a barrel, that's $36 million. $50, $18 million. Say it's available 6 months of the year, $9 million plus fuel savings, simply by adjusting the set point of a temperature controller. So 0 CapEx, rate of return is amazing. You can make your companies more money starting today if you want to.